Thank you very much. Before to start with my speech, I want to thank Ken for the very kind invitation, and I'm very happy to be here. I thank you, all of you, for the warm hospitality, and in particular Masaomi and Tomoki, because I already know these two guys because we are working on some projects together with Ken. And yeah, so, and I'm happy because you are giving me the possibility to present a project that I personally started almost 10 years ago. And this project has the aim to link the morphological, physical and chemical properties that we observe today in supernova remnants to the physical properties, the physical processes governing the supernova explosions, the pan-supernova explosions, but also to the nature of the progenitor stellar systems. Of course, I mean, this is a project involving many institutes dispersed in the world, and in particular, it includes institutes in Europe, in Asia, including also your institute, and in the United States. Okay, the project focuses mainly on the remnants of core-collapsed supernovae. So I will talk of core-collapsed supernovae. And as you know, these objects are beautiful extended sources, which are characterized by rather complex morphologies, and intricate patterns of shocks interacting with each other, interacting with the stellar debris, and you may also recognize a vast variety of different morphologies and structures in these supernova remnants. So the problem here, what is the reason of this variety and complexity in supernova remnants morphology? And well, to some extent, we expect that this complexity originates and reflects pristine structures and features produced originating during the complex phases after the collapse of the stellar core. In fact, numerical simulations as those that I'm showing here show that soon after the core collapse several stochastic processes occur, and these processes, like the standing accretion shock instability or the convective overturn because of neutrino heating, are responsible for the development of large-scale instabilities. And so the question is it possible that these post-explosion instabilities are the main responsible for the asymmetries that we observe today in supernova remnants? This object is very popular. This is the remnant, the supernova, a galactic supernova remnant called Cassiopeia A. If you look at the observations tell us two important things. The first is that this remnant is characterized by a very complex structure. The distribution of ejecta is highly inhomogeneous. The chemical distribution of the ejecta is also highly inhomogeneous. The second important thing that these observations tell us is that the remnant seems to expand through a medium which is almost spherically symmetric. So if this is true, this means that all these asymmetries that we observe today in Cas-A originated from the supernova explosion. And this means that the large-scale asymmetries that numerical simulations suggest us may be the main responsible for the features that we observe today in Cas-A. The point here is that looking at the asymmetries in supernova remnants, we may have the quite unique possibility to probe the physics of supernova explosions. And we may gain physical insight from the asymmetries that occur during the supernova explosion. And what about the progenitor stellar system? The question here is it possible that the final remnant morphology and structure is linked also to the nature of the progenitor star? Well, it's difficult to answer this question. However, again, numerical simulations tell us that the environment in which the collapse occurs can be rather complex, with turbulence, mixing of different ejecta layers, and 3D simulations show also that several instabilities may easily develop. So the core collapse occurs in a very complex environment. So the question now is it possible that this environment affects the way post-explosion asymmetries develop, I propose a simple experiment for you. Try to consider different objects and smash these objects on the ground. These are the remnants of a raspberry, egg, apple, and tomato. These remnants look very differently. And the reason for these differences is basically due to the structure, the internal density structure of these objects. Fortunately, we don't need to do these experiments at home because, again, we have numerical simulations. And then these numerical simulations in particular show that the structure of, in this case, nickel-rich ejecta is affected by the environment in which the explosion occurs. In particular, each of these rows corresponds to a different progenitor star, and the supernova has similar explosions energies. And you see how different can be the structure of the post-explosion asymmetries depending on the structure of the environment. This is quite obvious to understand because the explosion grows up in an environment which is characterized by different densities. So these affect the way the asymmetries develop. In the previous slides, I have shown that these post-explosion asymmetries can be responsible for the final structure of the remnant. So here the question is it possible from these asymmetries to gain knowledge about the internal structure of the progenitor star at the time of collapse? And here there is actually the second point. The asymmetries in supernova remnants may offer the possibility to investigate also the nature of the progenitor star. And finally, of course, everybody expects that the remnant morphology, the remnant structure, reflects also the environment, the circumstellar medium, the interstellar medium through which the blast wave expands. This is true for young supernova remnants S87A. The morphology of this remnant is characterized by a ring-like feature. And this is basically due to the fact that the remnant is interacting with a highly inhomogeneous circumstellar environment. But this is true also for more mature supernova remnants as the Cygnus loops. The observations show that there are clear indentations, and these are signatures of interaction of the blast wave with isolated clouds, dense clouds of the interstellar medium. And this can be particularly true for remnants as IC443, the so-called jellyfish nebula, because this morphology is basically due to the fact that the blast wave is expanding through a highly inhomogeneous environment characterized by several atomic and molecular clouds. And this ambient environment is the main responsible for the jellyfish shape of this remnant. So again, asymmetries in supernova remnants in this case offer us the possibility to reconstruct the geometry, the density structure of the environment through which the blast wave is expanding. And in the case of young supernova remnants, this environment is the circumstellar medium that was captured by the wings of the progenitor star. So this means that we have the possibility to constrain the mass-loss history of the progenitor star and therefore to gain knowledge about the final phases in the evolution of the progenitor star. So my conclusion in this first part of the talk is that observations of supernova remnants can be very rich sources of information on the parent supernovae and on the progenitor stars. And these actually make the study of the so-called progenitor supernova remnant connection an essential step to open new exploring windows on the physics of this object. If I convinced you that it can be important to study the link between these three phases in the evolution of stars, the question is, okay, is it feasible? Is it possible? What can I do to study this connection? Well, studying the path from the progenitor star to the supernova and supernova remnant can be a rather difficult task because it requires for sure a multi-physics approach, because we have to describe the evolution of progenitor stars from the cradle to the grave, from their formation to the core collapse. And we have to describe the complex phases in the evolution of the supernova. And after the shock breakout at the stellar surface, we have to describe the expansion of the remnant through an inhomogeneous and magnetized environment. And since we know that supernova remnants are sources of cosmic rays, we have to take into account also the acceleration of particles. Why? Because the acceleration of particles modify the shock dynamics, which means to modify the structure and morphology of the remnant. They contribute with non-thermal emission to the final morphology of the remnant. So we have to take into account also this effect if we want to link the morphology, the physical and chemical properties of the remnants to the progenitor supernova and progenitor stars. But this task, to follow the path from progenitor star to supernova and supernova remnant, requires also a multi-scale approach, because the core collapse occurs on length scales of the order of 10 to 9 centimeters, evolving on a time scale of the order of 1 second. But supernova remnants expand for several parsecs, and they evolve on time scales of the order of hundreds, if not thousands or tens of thousands of years. And finally, a multidimensional approach is also required, because asymmetries and isotropies, as I've shown, easily develop soon after the core collapse. And after the shock wave, the breakout of the shock wave of the stellar surface, the blast wave propagates through an inhomogeneous and magnetized environment. And hydrodynamic instabilities easily develop in all the phases that we are considering. And all these features are inherently three-dimensional. So they require a 3D description. And since, as I said, the asymmetries are messengers, they carry information about physical processes occurring during the supernova explosion. And so this means that we have to, if we want to decipher these observations, we have to describe all these features accurately. And another problem, another issue we have, all these features, all these effects, the effects of the progenitor star, of the supernova, the environment, are at work simultaneously. So we have also the problem to disentangle the different effects. We have to disentangle the initial conditions, which are the asymmetries developed soon after the explosion of the supernova, from the boundary conditions, which is the environment through which the blast wave expands, the remnant expands. So to take into account all these requirements, the approach we have developed is based on the coupling between three-dimensional supernova models and three-dimensional supernova remnant simulations. The supernova models include all the ingredients to describe the complex phases in the evolution of the supernova, including also an accurate description of the structure of the progenitor star. So this means that these models are also coupled to stellar evolution models. And this is an important step because these models provide the initial conditions for supernova simulations, the density structure of the star at the time of core collapse. Supernova models usually stop soon after the shock breakout of the stellar surface, which means a few hours after the core collapse. And they provide the initial conditions to supernova remnant simulations. And again, the supernova remnant simulations have to include all the ingredients to describe the metamorphosis of a supernova in a supernova remnant, the transition from a supernova in a supernova remnant. And they have to describe also the expansion of the remnant through the inhomogeneous environment. For this reason, it is important to provide an accurate and realistic description of the environment. This is feasible for specific objects thanks to constraints from observations. But this is feasible also for young supernova remnants in general, taking advantage again of stellar evolution model, because they can provide the mass loss history of the progenitor star. From the mass loss history, we can reconstruct or try to reconstruct the CSM through which the blast wave expands. An essential step here is to synthesize the observables. Thermal emission, non-thermal emission, the distribution of the ejecta, their chemical distribution, and this is important to compare the model results with the observations and get a feedback on the models. This is important to constrain the models. And once the models have been constrained, this can be used as a fantastic tool for the analysis and the interpretation of the observations, because they can be a powerful tool for deciphering the observations and extract information on the parent supernovae and progenitor stars. A few examples of application of this approach. And I want to start with the case of, to answer this question, what are the effects of the supernova explosion on the final remnant morphology? And to talk about this case, I consider again the supernova remnant Cassiopeia I mentioned at the beginning of my speech. As I said, observations suggest that the blastwave is expanding through an almost spherically symmetric wind of the progenitor star. If this is true, this means that all the asymmetries that we observe in this object were inherited from the supernova explosion. And this makes Cassiopeia a unique laboratory to study the supernova remnant connection. In addition, this object has been studied in excellent details by several authors, including Danny Milisavljevic and Rob Fezen. They were able to reconstruct the structure, the 3D structure of the ejecta from the analysis of the observations.
You don't mind for somebody totally ignorant and know nothing about supernovas. In here, are we looking at the snowplow phase of the stellar explosion?
You mean in the observation?
Yes.
Yeah, this observation here basically is showing the blast wave after 350 years of the explosion. The center of the explosion was more or less at the geometrical center of this remnant. It's located more or less here.
But is this a set of Taylor phase? Or
sorry?
Is this a set of Taylor stage?
Oh, this is this is in a set of Taylor phase.
But
because
most of the material is interstellar.
The material which is shocked here is mainly circumstellar material.
Circumstellar.
Yeah,
yeah.
Because this remnant is pretty young, 350 years old. And
circumstellar means it's the stellar wind.
The stellar wind, yes.
So this is you're seeing the chemical composition of the stellar wind here.
Well, actually, in this case, the supernova was a stripped envelope supernova. So most of the emission originates from the shocked ejecta. So, for instance, I show you an image. Oops. Okay. In this image, the green region that you see here is material rich in silicon. And this is ejecta material producing a sort of jet-like feature here. Okay? So these are ejecta. Also, from the other observation, you see this red area here, this red area here and here, which are basically the blue regions that you see here. This is material rich in iron. And these are again ejecta. So if you look at this remnant, in this particular remnant, you see that it is rich of asymmetries. And all these asymmetries are due to ejecta. The blast wave is the remnant outline is almost spherical if you exclude the protrusion of this jet. And this is one of the reasons why the people say that the remnant is expanding through the spherically symmetric wind of the progenitor star. The expansion rate and the overall morphology of the remnant are both compatible with the remnant expanding through the wind of the progenitor star. However, this is not entirely true, I will tell you later. But on average, this is the case. If you look at the forward shock, you have some emission from the forward shock, but it is not in the radiative phase still, because the material accumulated is not enough to produce a significant emission from the forward shock. So this remnant is ejecta dominated. And in fact also, this is
the emission is ejecta dominated.
Yeah, the emission is ejecta dominated.
But the momentum is wind dominated.
The momentum is dominated by the blast wave propagating through the wind of the progenitor star, yes, exactly. This is actually, and this is the reason why this object is interesting, because the fact that we had a stripped envelope supernova allowed asymmetries developed soon after the core collapse to expand freely without any limiting effect due to the hydrogen envelope of the progenitor star. So they were free to expand, and now this is the reason why we can clearly see all these post-explosion asymmetries producing.
The composition is reconstructed from line measurements.
Line measurements, yes.
But if you took, let's say, a hydrogen or helium tracer, it would be much more homogeneous.
Yes, it is much more homogeneous, and also if you look at light elements, this is much more homogeneous.
And yes. It would be mostly dominated by the wind.
And this is mostly dominated by the wind, the shocked wind, yeah. Yeah. Okay, so from the observations, it was possible to reconstruct the 3D structure of the ejecta. And as I already said, this structure is characterized by 3 iron-rich regions. 2 silicon-rich jets, one is this one I mentioned before. There is also a counterjet not so visible as this one. And there are also rings encircling the iron-rich regions. And if you look at these shocked ejecta, they are arranged in a sort of torus-like feature. So this is also the reason why the people say that talk of a thick disk morphology of ASIAA. So we wondered how it is possible to produce this highly inhomogeneous distribution of the ejecta. And in a first attempt, we coupled together a supernova remnant simulation starting from a spherical supernova explosion plus post-explosion asymmetries that were parametrized. In particular, soon after the shock breakout, we prescribed post-explosion asymmetries characterized by parameters like the density contrast, the velocity contrast, the size, and the initial position with respect to the center of the explosion. Then we have explored the space of parameters, searching for a set of parameters which is able to reproduce, more or less, the structure of the observed ejecta. This movie shows the results for our favorite model. So you have shocked ejecta, unshocked ejecta, in blue iron-rich ejecta, and in red silicon sulfur-rich ejecta. This yellow sphere is the nominal position of the rubber shock, and these transparent panels are real observations of ASIAA in the optical and X-ray band in the same scale as the model. So in this way you can compare directly the observed morphology with the modeled distribution of the ejecta. And in particular, thanks to this model, it was possible to constrain the average properties, physical characteristics of the post-explosion anisotropies that can be responsible for the structure of ejecta observed in ASIAA. And this was an important step. Now it was 10 years ago that we have done these simulations, because this means that we are able to constrain the average energies and masses of the post-explosion asymmetries. And this information can be used as a guide for explosion models, supernova explosion models. 1 year later, the group at Max Planck Institute for Astrophysics has analyzed a sample of 3-dimensional simulations of neutrino-driven core collapse supernovae, searching for a case which is able to reproduce the basic properties of ASIAA. These simulations differ from the previous one because now the post-explosion asymmetries are not prescribed, but they develop self-consistently, naturally, from stochastic processes occurring soon after the core collapse. And they found that one of the models that they analyzed produces these 3 nickel-rich fingers that may correspond, roughly, to the 3 iron-rich regions observed in ASIAA. Because as you know, during the first year of evolution, the nickel decays in cobaltum, which decays in iron. So all these nickel-rich ejecta at the age of ASIAA are iron. This was an important result, because this is a way, these simulations unfortunately stop 1 day after the explosion, so they are not able to follow the evolution till the age of ASIAA, but nevertheless, they show that the major asymmetries observed in Cas-A can be reproduced with the neutrino-driven core collapse supernova. Then we decided to join forces to couple our supernova remnant simulations with these neutrino-driven supernova explosion. And in this way, we produced the first and currently the only self-consistent model which is able to describe the evolution from the core collapse to a supernova remnant at the age of 2000 years, so even more than Cassiopeia A. So this is the result of the neutrino-driven core collapse supernova at the age of 20 hours after the core collapse. You see the forever shock, the forward shock, and during the first year of evolution, this nickel decay in cobaltum, which decays in iron. So all these ejecta transform in iron-rich ejecta. And due to this process, heating is released locally, producing the so-called nickel bubble effect. At the age of 30 years, these plumes rich in iron starts to interact with the reverse shock. This is the time when the iron-rich regions we observe today in Cas-A started to form. And this is the distribution of iron-rich ejecta at the age of Cas-A. And you see that the iron-rich regions are characterized by several hydrodynamic instabilities. And these instabilities are the main responsible for ring-like crown structures that are observed in the iron-rich regions of Cas-A. As for the unshocked ejecta, these are characterized by several voids and cavities due to the nickel bubble effect during the first year of evolution. And this is exactly as it is observed in Cas-A. And since actually we have three plumes expanding, the ejecta are mainly produced in a plane. And this is the reason for the thick disk morphology of Cas-A that is inferred from the analysis of the observation.
These hydrodynamic instabilities are due to the neutrino driving, convective
No.
reversal of neutrinos.
No, the plumes, the large-scale features are due to the neutrino, to the convection. But all these instabilities are Rayleigh-Taylor instabilities developing close to the contact discontinuity because of the interaction of the remnant with the wind of the progenitor star. So all the instabilities that you see here, these hydro instabilities, are Rayleigh-Taylor and Kelvin-Helmholtz instabilities developing close to the contact discontinuity. The plumes, the three extended plumes that we have soon after the shock breakout, those originate from stochastic processes occurring soon after the core collapse. Yeah, and yes, later there was also the structure of the ejecta at the age of 2000 years. Of course, we will be not here to see if my prediction is correct, fortunately. But this remnant at the age of 2000 years can be compared with other supernova remnants more evolved than Cas-A, as for instance G292, which is a sort of cousin of Cas-A with an age between 2000 and 3000 years. So this means that it is possible to use the simulation also at later stages.
The instability is on the contact discontinuity between what's the different chemical elements, between the iron layer and some other layer.
Yeah, of course, I mean, you have the relative instability at the contact discontinuity develops because of the interaction with the circumstellar medium. And you have a mixture of different layers, and of course they interact with each other.
I mean, to get any of these instabilities, you need different specific densities, different
yes,
chemical densities,
yes,
molecular weights.
yes.
And then you put the low, and you've got the more higher molecular weight material on the inside.
Yeah.
And you've got the lighter material
yes.
on the outside, and
yes.
you've got an acceleration going inward.
Yes, exactly. But this is basically
inverse.
Yeah, but this is basically due to the fact that you have dense ejecta expanding through a low density medium, which is the CSM. So in general, actually, these instabilities are not peculiar of this model. All supernova remnant simulations show the development multidimensional, of course. You need to have at least 2 dimensions. You see the development of hydrodynamic instabilities at the contact discontinuity. And this is basically due to the expansion of the ejecta through the ambient environment. So this is not peculiar of this particular model. All supernova remnant simulations show these instabilities. What is peculiar in this model is the initial condition, because we are not starting from a spherically symmetric explosion, but we are starting from a non-uniform distribution of the ejecta, which is not arbitrary, was calculated with a supernova explosion model, in which the stochastic processes occurring soon after the core collapse produce these large-scale asymmetries. So the important point I want to stress here are not these instabilities, these hydro instabilities, but the fact that you have 3 extended iron-rich plumes that at the age of 30 years start to interact with the reverse shock. You produce these shocked ejecta rich in metals, iron, titanium, and so on. And the other point I didn't discuss here is that these plumes are faster than the outer envelopes made with other elements, and they are able to protrude through these other kind of ejecta. And in fact, in the iron-rich regions, you see that the iron is at larger distances from the center of the explosion with respect to silicon, sulfur, even oxygen. So there was an inversion of ejecta layer, and the plumes produced by stochastic processes occurring soon after the core collapse are then responsible for this inversion of the ejecta layer. And the inversion of ejecta layer is observed in Cassiopeia A. So this means that these processes are able to produce these features. Yes?
So I have a question about this core collapse supernova progenitor, because you probably cannot make a jet feature in the observation. This is one point. The second point is that you initiate with a three plume, the progenitor, for neutrino-driven explosion.
Yeah.
But from your simulation, I feel those plumes actually will be diluted due to the later radiator instability in the mixing.
Yeah.
So actually sort of destroy the plume.
Yeah.
When you evolve.
Yeah.
So I would see there's still some kind of gap, like a.
Yeah. Okay. The first point was about the jet. Yeah. Of course, I mean, this neutrino-driven supernova explosion is not able to produce the jet-like feature. And however, if you look at the energy budget of the jet, this is much lower than the energy budget of the supernova. What we think, because of course, I mean, the supernova explosion model was developed by the group at Max Planck Institute. So I discussed with this group, and we strongly believe that the silicon-rich jet was not produced during the core collapse, but it was produced during the phases after the core collapse, probably, and this is probably due to accretion of mass on the newly formed neutron star, proto-neutron star, yeah. So this is actually what we think. Of course, this is pure speculation, but this is our idea. The fact that you have also silicon-rich jet, but in the silicon-rich jet you don't see any iron, means that this is something different from what created the iron-rich regions. The iron-rich regions were created during the supernova explosion, and the plumes originated from the heating by the neutrinos and the standing accretion shock instability. So the jet, yeah, you're right, the jet cannot be produced by this particular model. This means that something is missed, and what is missed in this model is a process responsible for the jet after the core collapse. Your second question was about the stripped envelope.
May disappear.
Yeah.
Later.
Yeah. Well, we know that the progenitor star of Cas-A was a stripped envelope star. We know that from several lines of evidence. One is the comparison with 93J, which is considered to be a sort of twin of Cas-A, and that was a stripped envelope supernova, by comparing the spectrum of this supernova observed with the echo of the spectrum of Cas-A, they basically superimpose very nicely. So this means that the supernova that originated Cas-A was a stripped envelope supernova. Another point, of course, I mean, in this case it was used a stripped envelope progenitor star. The group at Max Planck has also developed the supernova including the envelope, the hydrogen envelope. If you have the hydrogen envelope, the post-explosion asymmetries that develop soon after the core collapse, these iron-rich plumes, can be strongly damped, limited when they start to propagate through the helium and hydrogen. And these actually limit the presence of large-scale asymmetries when you look at the final remnant. And this is actually the reason why Cas-A is a so unique laboratory for studying the physics of core collapse supernovae. Because thanks to the fact that the progenitor was without this envelope, we have the possibility to see the post-explosion asymmetries so well developed that were free to expand without any damping by the hydrogen and helium envelope of the progenitor star. So this is one of the reasons why we decided to consider this object. And this is the reason why this object is so well studied, because it's one of the closest supernova remnant. We can see it is young, so this means that the imprint of the supernova explosion is still, it is possible to identify the fingerprints of the explosion in the remnants and so on. So, the conclusion here is that basically this model allowed us to show that the major asymmetries observed in Cas-A can be explained naturally with a neutrino-driven supernova explosion, except for the jet, of course, and that this ejecta structure originates from stochastic processes that develop during the first seconds of the supernova blast wave. And I think that these results is amazing and fascinating, because this means that today, 350 years after the supernova explosion, we are able to identify the fingerprints of processes that were at work soon after the core collapse deeply in the heart of the progenitor star. Okay, the second point I want to discuss are the effects of the progenitor star on the final remnant morphology. And in this case, I will consider the case of 87A. Because as you know, this object is also characterized, this remnant is also characterized by several asymmetries. The most prominent is the ring-like feature I already mentioned, but this ring-like feature, as I said, is due to the interaction of the blast wave with the inhomogeneous environment. So I will not focus on this ring-like feature, but on asymmetries that characterize the still unshocked ejecta. 1-2 years after the supernova explosion, it was possible to measure lines of iron, and these lines are with an asymmetric profile. In particular, they are redshifted to velocities of about 300 kilometers per second, redshifted, and with the wings extending up to 3000 kilometers per second. So this means that we have metal-rich, iron-rich ejecta on average fastly traveling away from the observer. 20 years later, new star observations revealed the lines from the decay of titanium-44, and again this line is redshifted with velocities of the order of 700 kilometers per second. So again, showing that we have metal-rich ejecta on average propagating fastly away from the observer. And finally, ALMA observations are allowed to reconstruct the 3D structure of molecules, carbon monoxide and silicon monoxide, and these are arranged in a sort of torus-like feature, which is oriented more or less perpendicularly to the plane where the dense equatorial ring is located. So all these lines of evidence suggest that the explosion in 87A was highly asymmetric. And this means that we should see large-scale asymmetries. Actually, these asymmetries reflect the large-scale asymmetry in the explosion of 87A. At the beginning of my speech, I said that if we look at these post-explosion asymmetries, we may try to get some insight on the structure of the progenitor star at the time of collapse, so we can gain knowledge about the nature of the progenitor star. So we wondered if in the case of 87A this is possible. And to do this, we have coupled together different stellar evolution models, supernova models, and supernova remnant simulations. As for the stellar progenitor models, we considered three cases. The case of a blue supergiant that was used in the past in the literature to reproduce the properties of the progenitor star of 87A. Because in this case, the progenitor star of 87A was observed. And this means that we have observations of the progenitor stars, of the supernova, and of the supernova remnant. This is the reason why this object is so interesting. Then we considered another interesting case, and we know that it was a blue supergiant. The second case is again a blue supergiant, but now resulting from the merging of two massive stars. And this model is very interesting because this model is able to reproduce the basic properties observed in the progenitor star of 87A. In particular, its effective temperature, its luminosity, so its position in the Hertzsprung-Russell diagram, and also some of the anomalies, chemical anomalies, that were observed in this object. And finally, we considered as a progenitor a red supergiant. And you say, you are wrong. I mean, we know it was a blue supergiant. Why wasting your time in considering also a red supergiant? Well, we consider also a red supergiant to have a model which is certainly wrong, to check how sensitive is the remnant on the structure of the progenitor star. So we have three cases here. These progenitor stars provide the initial conditions for supernova remnant simulations. And in particular, these simulations were performed by Masaomi. You have a core collapse supernova. We assume that the explosion was bipolar, highly asymmetric, and there are two main parameters regulating this asymmetry. One parameter is basically the ratio between the deposition of energy at the poles and in the equatorial plane, and another regulates basically the ratio between the energies deposited at the two poles around the collapsing core. Masaomi has explored a space of parameters, searching for a set of parameters which is able to reproduce the line profile of iron observed 1-2 years after the supernova explosion. So from these simulations made for these three stellar evolution models, these simulations are used as initial conditions for supernova remnant simulations. The starting time here is again about 1 day after the supernova explosion. In this case, the circumstellar medium highly inhomogeneous was parametrized. We have explored the space of parameters, searching for a good set of parameters which is able to reproduce the main observables of the supernova remnant. This movie shows the distribution of iron-rich ejecta 1-2 years after the supernova explosion. The color indicates the velocity along the line of sight. So in blue, material propagating toward the observer. In red, material propagating away from the observer. For the blue supergiant, evolved as an isolated star, the blue supergiant resulting from the merger, and the red supergiant. We synthesize.
Merging means it's a blue straggler that explodes.
Sorry?
Merging means you put a blue straggler. It's in already new radiative equilibrium before it explodes.
No, this is there was actually, we consider progenitor stars, then we consider the supernova explosion, and we follow the evolution of the ejecta. In particular, these are the ejecta rich in iron at the age of 2 years.
Yes, but your progenitor star, in the case of the merger remnant,
yeah,
and you allow, but the merger happened 1 million years ago. So
it happened 20,000 years before the explosion.
20,000. That's
yeah.
very recent. So you're not yet in.
Yeah.
You're not yet in radiative equilibrium.
Well, okay. In the case of the progenitor star in the merger scenario, The idea is the following. In particular, actually, this was an idea that was suggested before, and that was confirmed by this model that is developed by the group in Japan, Urushibata and collaborators. And basically, you have, originally you had two massive stars with masses well above 10 solar masses. Now, one, I think it was 9 solar masses and the other 23. I don't remember exactly the numbers. Then you had the merging at some point of these two stars. There was a common envelope phase, and then 20,000 years before the supernova explosion, the merger produced a blue supergiant, and 20,000 years later, the star exploded. And in fact, actually, during this phase, you produced the high homogeneous circumstellar medium, because during the common envelope phase, you produced a sort of torus-like dense feature around the progenitor star. The blue supergiant, with the fast and tenuous wind, pushed away the previous wind, slow wind, from the red supergiant phase and the common envelope phase, producing the hourglass-shaped morphology of the circumstellar medium. And there is a nice simulation by Morris and Posiadlowski, published in 2007, showing how the circumstellar medium formed because of these different phases. And also for the circumstellar medium, you need, this is a cross-check for the model, for the stellar evolution model, you need 20,000 years of a blue supergiant phase to push away the plasma to the distance where it is observed today, at the time of the explosion. So from these simulations, we synthesized the iron lines, and we compared the iron lines with those observed. And the model that best reproduces the broadening and shift of the lines of iron is the one considering a merger. So this is the model best reproducing the observed lines of iron. This is the distribution of titanium 20 years later. The color is again the velocity along the line of sight. The ring is the nominal position of the rubber shock. This is not in the same scale of the iron. And we synthesized also the lines from the decay of titanium-44. The black Gaussian is the Gaussian fitting the observed line. The gray zone is the 90% confidence area for the position of the peak and the width of the Gaussian fitting the data. And the red Gaussian is the synthetic line from the model best reproducing the observations. And again, this model is the one assuming a merger progenitor, a blue supergiant resulting from the merging of two massive stars. So basically, in this way, we were able to I characterized the bipolar explosion and also its orientation with respect to the line of sight, and we predicted that we have a clamp rich in iron and titanium propagating to the north toward the observer, and a more massive clamp of iron and titanium propagating southward away from the observer. So, and we, of course, we have seen that the best progenitor star to reproduce the data is a progenitor star assuming the merging of two massive stars. What is interesting is that, because this was published in 2020, 1 year ago, thanks to observations of JWST, it was possible to reconstruct the 3D structure of iron-rich ejecta. And this is the result by Josephine Larson and collaborators. They found two clamps of rich in iron. One propagating to the north toward the observer, one propagating to the south away from the observer, and the one propagating to the south is more massive. So this was a very nice confirmation of what we have predicted. The main difference here is that the clamp propagating to the south is not aligned with the center of the explosion and the other clamp. It's slightly tilted in this way, but this is due to the fact that we have assumed a very idealized bipolar explosion. We expect that if you have stochastic processes again soon after the core collapse, we know this from magnetorotational supernovae, you may have some deviations from an ideal bipolar explosion. And another problem with our model is that it seems that the observation suggests a more extreme asymmetric explosion than the one that we have simulated. Okay, as for the molecular structure, this is the structure, the 3D structure of molecules inferred from the analysis of ALMA observations, and this is what we found. Look at the red supergiant progenitor. This model completely fails in reproducing the observations, which is a good news. It means that the supernova remnant keeps memory of the structure of the progenitor star, is sensitive to the structure of the progenitor star. The two blue supergiant progenitor reproduce a torus-like feature, but this is not, in my opinion, the most important result. The important result here is that this torus-like feature is oriented and has a sides which are both compatible with the sides and orientation of the torus inferred from the analysis of the observations. So this means two things. That looking at these structures, not only these structures contain, encode the fingerprint of the progenitor star structure, but they include also the fingerprint of the supernova explosion, because the bipolar explosion we considered is oriented along the symmetry axis of these torus-like features. And the two clamps of iron observed with JWST are oriented exactly along the symmetry axis of this torus-like feature.
You already said that the simulations, when they are always asymmetric, but then if you run multiple simulations in any one of these scenarios, couldn't you get crossover?
Well, the fact is that in these simulations, we have parameterized the explosion, and we assumed a perfectly bipolar explosion.
Yes, but you already said that.
Yes.
In reality, they may not be, in which case...
Yes. Yes, of course. In this case, you may produce many features that are observed. But if you look at the large-scale structures, you can recover the large-scale structures of due to the explosion. Like for instance, of course, I mean, if you look at these observations, and you have also to take into account that in the observations, you have also some indeterminacy or some difficulties in reconstructing the 3D geometry of the torus-like feature, for instance. But of course, I expect that you may have several instabilities that may not be considered accurately in the simulation, also because these features are in the innermost part of the remnant, and of course you may have issues related to the spatial resolution of the simulation that we are considering. So of course, I mean, what I expect is that considering a more realistic simulation, like for instance a magnetorotational supernova explosion, in which you have stochastic processes taken into account consistently, probably you may recover much better all the details of that you observe in the structure of 87A. But of course, when you have stochastic processes, this means that you have to produce a large number of simulations, because as it was done for CAS-A, because of course, I mean, since you have stochastic processes, you may produce different asymmetries that may not correspond to the asymmetries that you observe in 87A. Okay, final point I want to discuss, the effects of the ambient environment. And since I mentioned the case of the ring-like feature observed in 87A, I want to start my discussion from this case. Of course, this is basically due to the fact that the explosion occurred in a very inhomogeneous environment, which consists in an extended H2 region. This is a section, and a very dense equatorial ring, and this is tilted by 45 degrees with respect to the line of sight. These observations in the X-ray band show the ring-like morphology, and you see that the ring expands as the blast wave propagates through the H2 region. At some point you see the brightening when the blast wave starts to interact with the dense equatorial ring. This movie shows the X-ray emission synthesized from our best fit model, the same model that is able to reproduce the lines of iron, titanium, and the distribution of molecules. Soft X-ray emission in this band, hard X-ray emission in this band, the contribution to emission from different plasma components. In blue, the shocked material from the H2 region, in red, the shocked material from the ring, in green, the shocked ejecta. And this is the symbols are the observed like curves in the soft and hard bands. The solid line is the synthetic like curve from our model. The other lines are the contribution to emission from the different plasma components. Again, shocked ejecta, shocked H2 region, and shocked ring. So in this way, we were able to identify 3 different phases in the evolution of AT7A. A first phase during the first 13 years in which the emission was dominated by shocked H2 region and shocked ejecta. An intermediate phase in which the emission was entirely dominated, especially in the soft band, by the shocked ring, and you see it in red here. And finally, our model predicted in 2020 that we were entering in a new phase in the evolution of AT7A, in which the emission will be dominated by shocked ejecta. And this is a very interesting point, because this means that in the X-ray band we will have the possibility to investigate the chemical composition, the structure of the ejecta.
This is free.
Which one?
Your movie.
Free?
Emission.
The emission, this is thermal emission. So actually you have everything. You have, I mean, it is dominated by emission lines.
By lines?
Yes.
But then with Chandra you can see the lines?
No, but this is integrated in this band.
I know, but you could look at the spectrum too.
Yeah, of course. I mean, if you look at grating spectra, I don't show you here, but we compared also the model with grating spectra, and we are nicely reproduce all even the line profiles in the grating spectra. Yeah, but of course, I mean, this is thermal plasma at temperatures of the order of tens million degrees electron temperature. And this is, of course, integrated emission, and this is also integrated emission. And here you have observations from different instruments. When you integrate, of course, I mean, you have to take into account also the lines, because most of the emission originates from the lines. So when you integrate between 0.5 and 2 kV, you have to integrate the contribution of all the lines included in this band. Okay? Okay. So this was our prediction. The model here was constrained with observations collected till 2016. But we continued to monitor AT7A until last year. So the question is, can the model reproduce also the new observations? This is the result. The model continues to reproduce the new observations, but what is important here is that the fact that you have a sort of plateau here is basically due thanks to the contribution of shocked ejecta. So our prediction that the emission now will be dominated by shocked ejecta is nicely confirmed by the fact that you have this plateau and you have not a decline of the soft X-ray emission.
See, but the ring has much less iron, presumably.
Sorry?
The ring has much less iron, for example.
Yeah, but this is actually integrated emission.
I know, but you have data on
yes.
the lines too.
Yes. No, okay.
I mean, prediction. You can just
Yeah. No, actually, this is difficult because currently the ejecta that are shocked are the outermost ejecta, and from our simulation, we have seen that these outermost ejecta are basically the hydrogen and helium envelope. So it is not rich of iron at all. So this is actually the main problem, is to disentangle the effect of shocked ejecta from the effect of shocked CSM, because currently the chemical composition is very, very similar. So you cannot distinguish if you look at the abundances. But 1 year ago we published a paper where we show how you can distinguish between shocked ejecta and shocked CSM, which is actually based on the velocity, because the shocked ejecta are much faster in this case. And if you look at the line profiles, you have two different profiles. You have two different components in the line profile, a broad component and a very narrow component. So the narrow component is due to the CSM. The broad component is due to the ejecta. So and this is actually, we proposed an observation to be done with CRISM, because there is a possibility of very high spatial resolution, because according to our preliminary simulations of the spectra of CRISM, it will be possible to disentangle the contribution from CSM from the contribution from the ejecta. But just looking at the line profile, not the abundances, because unfortunately at the time of explosion the star had a very massive envelope of hydrogen. At the explosion we had 18 solar masses of star and 9 solar masses are in the hydrogen envelope. So it's a really thick envelope. JWST observation of 87A. This was collected with JWST. It was published, actually there is a paper in press that appeared on Archive a couple of weeks ago. And so this is the observation of 87A in 2023. Our simulation, published in 2020, covered 50 years of evolution. So we predicted the evolution of 87A till 2037. Question: how our model is able to match this observation? And this is the result. This is the configuration predicted by our model in 2023. So basically, it is possible to use our model of 87A to explain all the features that are visible in 87A. However, and probably this is the most interesting point, there are some discrepancies. Discrepancies between model and observations are opportunities, because this means that something is missed in our model. So we have the opportunity to gain knowledge if we understand the origin of the discrepancies. And in particular, I want to show you one of these discrepancies. Look at these two clamps here. These are the clamps rich in iron, and these are the clamps predicted by our model. If you look at the observations of 87A, what do you see? These clamps are much more extended. So this means that in the explosion, we were not able to describe accurately the explosion itself. And this means that a more collimation in the explosion would be necessary. And a possible mechanism which can produce a collimated explosion is a mechanism based on a magnetorotational supernova, which is plausible because we had the merging of two massive stars, so we have a lot of angular momentum. It is possible that you have strong magnetic field, so if you have these two ingredients, magnetic field and high rotation, you may produce a magnetorotational supernova. This is, however, a work in progress. This is something that we want to investigate in the near future. Another point that we want to investigate, actually we had a very nice discussion with Filip Posiadlowski a week ago, also with Ken. This is actually the model of the circumstellar medium developed by Morris and Posiadlowski and published in 2007. This distribution of the circumstellar medium was calculated self-consistently from the merging of two massive stars. So we are wondering how the model in which the ambient environment was parametrized react to the interaction with this ambient environment. And this is something that hopefully we will investigate in the future. Okay. I'm very close to conclude. Because in the case of 87A, you can say, okay, well, in the case of 87A, the interaction with the CSM is quite obvious, because the CSM is so dense and inhomogeneous that we clearly see the effect of the CSM on the final remnant morphology. And so I want to discuss the case of Cassay, because I said several times during my speech that the remnant is expanding through the spherically symmetric wind of the progenitor star. Is it true? Well, this is an observation, a radio observation of a Cassay, and I suggest to do this simple exercise. Try to fit the remnant outline with a circle. If you do the same with the reverse shock, you obtain this result that was noted the first time 20 years ago by Gottolf and collaborators. The point is here that the two geometric centers of the reverse shock and forward shock are characterized by an offset. And if the remnant was expanding through a spherically symmetric wind, it is difficult to understand the origin of this offset. More interesting, if you look at the non-thermal emission in Cassay, you see that most of the non-thermal emission originates from the western side. Why? If the remnant was expanding through a spherically symmetric environment, the ejecta enters the reverse shock with similar velocities than here. This is not true. And this was proved a couple of years ago by Jakovinka and collaborators. They analyzed Chandra observations and they derived the azimuthal profile of the forward shock velocity and the reverse shock velocity. The forward shock velocity is almost around 6,000, 5,000, 6,000 kilometers per second. The reverse shock is around 3,000 kilometers per second, almost everywhere with one major exception. In the western side, the forward shock is traveling backward in the observer reference frame. How this is possible? I mean, if the remnant is expanding through a spherically symmetric environment, how it is possible? Some people suggested an asymmetric explosion. We have a model for an asymmetric explosion which is able to reproduce many of the features observed in Cassay. So, why not using this model and try to see if this model is able to reproduce this strange behavior of the reverse shock? So we derived from this model the azimuthal profiles of forward shock and reverse shock velocity. Result. Whoops. Please. Yeah? I don't know what is going on.
I want to have a meeting.
Ah, oh, sorry. Okay. We were close to close to solve the mystery, and yeah. Okay, I will try to continue without waiting for. If you try to derive also the reverse shock and forward shock velocities, in this case, you fail. It is not possible, in particular, to reproduce this minimum in the profile of the reverse shock. I'm sorry, but I don't know why I'm not able even to exit from. Okay. Yeah. Okay. I'm sorry. This is the first time that it happens. Yeah. Yes. Okay. Some spoiler. Okay. Okay. Now you can see that actually. So the model fails in reproducing this minimum. So something is wrong in this model, or something is missing in this model. Again, discrepancies can be an opportunity to gain knowledge. So if the explosion itself is not able to produce the asymmetry, who is the culprit? The CSM. So we wondered if a shell, an asymmetric shell in the circumstellar medium, is able to do the job. And this is, we explore the space of parameters. This is a model, as before, but now interacting with a circumstellar shell. This bluish region that you see here is the shocked shell, which is already engulfed by the forward shock. Let's try now to find the azimuthal profile of forward shock and reverse shock velocities. Aha! Now we are able to find the minimum in the reverse shock velocity, which is actually in where the remnant interact with the densest portion of the shell. Of course, I mean, our minimum is larger than that observed, but this depends on the density structure of the shell. The point here is that even in this case, in which it was not evident the interaction with an inhomogeneous environment, it is possible to gain knowledge about the mass loss history of the progenitor star. In fact, offset, this is what the offset observed, and this is the offset in our best fit model. Look at the green and red crosses. And the point here is not the offset itself, but the extension of the offset and the orientation of the offset in the space. This plot shows the velocity of the ejecta entering the reverse shock as a function of the position angle. The velocity is pretty low almost everywhere, below 2000 km per second, which is not enough to produce significant non-thermal emission, but where the remnant interacted with the densest portion of the shell, the velocities can be as high as 6000 km per second. And this may explain why most of the non-thermal X-ray emission originates from the western side of the remnant. So basically, the interpretation we have here is that this strange behavior of the reverse shock is considered to be a signature of interaction of the remnant with a dense asymmetric circumstellar shell. The forward shock interacted with the shell in the 19th century, and the reverse shock started to interact with the shell basically during the Second World War. Most likely, this is our interpretation, this shell is the result of a massive eruption from the progenitor star that occurred between 10 to 4 and 10 to 5 years before the core collapse, and we have estimated an upper limit to the mass, which is around 2 solar masses. Why this information can be important? Because, as I said, the progenitor of Class A was a stripped envelope supernova, and the hydrogen envelope that we want to remove is more or less these sides. So how this envelope was removed? Another point, our model with the shell suggests the presence of these features, holes in the shell. And when we published this paper, these holes were never observed in Class A. So it seemed to be a side effect of the idealized simulation. But now we have JWST observations. This is a paper recently published. And in these observations, it was found this feature called the green monster. And we found that this feature is shocked circumstellar medium. This feature is not ejecta. A zoom of this green monster. Do you recognize something? These are the holes produced by our simulations, and here you can find a comparison of observed features and modeled features. So there is some consistency. We are saying that these holes are in the shocked shell, and in fact these holes are found in the green monster, which is considered to be shocked CSM, Probably this green monster is the relic of the shell that encountered Casey almost 150 years ago. Thanks to the model, it is possible to explain the origin of these holes. These are basically due to the interaction of hydrogen instabilities at the contact continuity of the remnant with the shell, producing clamps that pierce through the shell, protruding through the shell, and producing these holes. Takeaway points, and I concluded because I think I was very, very long. Sorry for that. I have seen, basically, I discussed that the supernova remnant morphology and properties reflect several properties. They can reflect asymmetries inherited from the parent supernova, the structure of the progenitor star collapse, and the interaction with the inhomogeneous ambient environment. For this reason, deciphering multivalent observations of supernova remnants can be crucial to extract information about the complex phases in the supernova explosion. So, probing the supernova engine, we can obtain information about the nature of the progenitor stellar system and also the structure and geometry of the circumstellar medium, which means that we have the possibility to constrain the mass loss history of the progenitor star. And this is the reason why studying the progenitor supernova remnant connection has breakthrough potential to open new exploring windows on the physics of this object. How to do that? I hope I was able to convince you that the class of models I presented today can be a big help in linking supernova remnants to their parent supernovae and progenitor stars. However, and this is actually the challenge in this kind of exercise, deciphering observations may critically depend on the models, and this means that these models should connect consistently as much as possible the three phases in the evolution from the progenitor to the supernova and supernova remnant. And the second point, they should be based on solid observational facts. These models need constraints from observations because you have many parameters. These are complex models, so it is extremely important to have observational constraints because otherwise the validity of these models can be very poor. And this can be important today thanks to new observations collected with JWST, with CRISM, and other new generation instruments that highly require appropriate tools for their analysis and interpretation. So thank you very much for your attention.
Thanks so much. And sorry for being late.